Hello, students. Today, we're delving into the fascinating realm of alkali metals and their compounds. Alkali metals are unique in that they're found exclusively in compound forms within nature. Sodium and potassium, two notable examples, are quite abundant and can be found in various places, including Earth's crust, seawater, and even biological systems. Importantly, they are found as cations in ionic compounds. Let's explore further. Hello again, dear students. Today, we're delving into a specific aspect of chemical reactions involving alkali metals and hydrogen. In the context of alkali metal hydrides like Li and Na, hydrogen is fascinatingly present as the hydride ion, represented as He-. This hydride ion is not to be confused with the hydrogen ion, denoted as He+, which is formed when a hydrogen atom loses its electron. In these hydrides, hydrogen has gained an electron, creating the unique H-ion. Let's move forward to understand how alkali metals interact with water and witness a remarkable reaction. Hello again. Welcome back, my curious learners. Today, we're unwrapping the hidden treasure of energy transformations in the reactions of alkali metals with water. As alkali metals and water interact, a transfer of electrons occurs, resulting in the release of energy. This process transforms chemical potential energy into kinetic energy, leading to the dynamic reactions we observe. These reactions are known as exothermic, meaning they release energy into their surroundings. Can you feel the excitement as energy changes its form, right before our eyes? Stay with me as we journey deeper into the realm of chemical dynamics. Welcome back, my Hello again, young minds. Today, we're diving into the world of exothermic reactions and their intriguing characteristics. An exothermic reaction is one that releases a significant amount of heat during its course. Just imagine, these reactions can be so intense that they can even lead to ignition, producing fires or sometimes, in extreme cases, explosions. For instance, when hydrogen gas reacts with alkali metals like potassium, K, the heat generated is substantial enough to cause ignition, resulting in a fiery display. It's fascinating to observe how energy can be released in the form of heat during these reactions. But that's not all. Some reactions can be even more dramatic. Let's explore further. Hello again, young. Welcome to our next stop, Explorers of Knowledge. We're about to uncover the captivating reactions between alkali metals and oxygen. When alkali metals encounter oxygen, they engage in chemical reactions that result in the formation of metal oxides. Just think about the potential energy transformations happening here. Specifically, when lithium, Li, metal reacts with oxygen, it creates lithium oxide. Let's take a closer look at the reaction equation. 4Li1 squared plus O2 1H squared right pointing arrow 2 lithium oxide 1 squared, 7.19. This transformation not only showcases the interaction of elements but also demonstrates the conversion of energy. Isn't chemistry truly enchanting? And we're only getting started. Welcome to our next. Brace yourselves, knowledge seekers, as we unravel the intriguing world of reactivity. As we've seen, alkali metals have a penchant for engaging in fascinating reactions. However, did you know that the level of reactivity can vary among different alkali metals? It all boils down to ionization energies, a measure of how easily an atom loses an electron. Alkali metals with lower ionization energies tend to exhibit more vigorous reactions. Let's take a look at potassium, K, rubidium, Rb, and cesium, Cs. Due to their incredibly low ionization energies, Rb and Cs reactions are even more intense than that of potassium. This difference in reactivity showcases the intricate relationship between atomic properties and chemical behavior. Now, let's uncover another intriguing facet. Brace yourselves. Alright, students, let's explore the intricate dance between alkali metals and oxygen. While we might expect straightforward reactions, they often surprise us with their complexity. One captivating example involves sodium's interaction with oxygen. Instead of a simple reaction, we observe the formation of a more intricate product, sodium peroxide. This compound holds within it the O2 ions. The equation 7.20 beautifully encapsulates this process. Imagine the dynamic interplay of atoms and molecules as sodium transforms into sodium peroxide. Isn't it fascinating how chemistry unveils these hidden mysteries? Alright, welcome back, dear students. Today, we're delving into a fascinating realm of chemical reactions involving alkali metals and oxygen. Now, remember, we usually expect that when metals react with oxygen, they form metal oxides. However, the reactions outlined in equations 7.20 and 7.21 offer us a surprise. These equations showcase a different outcome, which might not be what we usually anticipate. As we've seen from our journey through equations 7.18 to 7.21, the alkali metals have an exceptional reactivity towards both water and oxygen. This unique reactivity sets them apart, and you might be wondering why. To prevent unwanted reactions, these metals are often stored in a clever way. They are submerged in a liquid hydrocarbon, like mineral oil or kerosene. This protective measure helps us harness the tremendous reactivity of alkali metals while keeping them safe from unwanted interactions. Now, let's move forward and unravel more about the intricate world of chemical reactions. Welcome back. Hello, students. Today, we're about to uncover a fascinating aspect of chemistry known as the flame test and emission spectra. Get ready to witness the colorful world of alkali metal ions and the mesmerizing dance of light they perform when introduced to a flame. It might sound surprising, but even though alkali metal ions are colorless, they emit distinct colors when exposed to flames. As we delve into this phenomenon, you'll learn about the reduction of these ions into gaseous metal atoms right within the flame. But what's truly captivating is what happens next. The intense heat excites the valence electron, causing it to leap from its ground state to a higher energy orbital, putting the atom into an excited state. And this excitement doesn't stop here. The atom then releases this accumulated energy in the form of visible light as the electron gracefully descends back to its lower energy orbital, and the atom returns to its relaxed state. This light emission is what we see as the characteristic colors. Just as we observed earlier with the line spectra of hydrogen and sodium, each element emits light of a specific wavelength, creating its unique color signature. Think of it as a chemical fingerprint in the form of light. For example, the famous yellow glow emitted by sodium at 589 nanometers serves as the foundation for sodium vapor lamps that you might have seen. But this captivating dance of light isn't limited to sodium alone. As we venture forward, you'll see how this concept extends to other elements and helps us unlock the secrets of their atomic makeup. So, let's explore the radiant world of flame tests and emission spectra together. Hello, students. Welcome back, students. Let's dive deeper into the mesmerizing world of flame test colors exhibited by various alkali metal ions. While these ions might start colorless, they transform into captivating hues when met with flames. Think of it as a chemistry-driven light show. Our journey through the color spectrum begins with lithium. When lithium ions are introduced to a flame, they paint the scene with a vibrant crimson-red glow. Next up is sodium, the element that graces us with its brilliant intense yellow light. You might have encountered this shade in sodium vapor lamps, lighting up streets and spaces. As we move along, we encounter potassium, which adds a touch of lilac or pale purple to the mix. Rubidium steps in with its own twist, emitting a captivating red-violet hue. And finally, there's cesium, casting a spell with its enchanting blue-violet color. Each of these colors is like a signature, telling us about the specific element present in the flame. Remember, it's all about the excitation and relaxation of electrons, a process that reveals the atomic identity of these alkali metals. So, keep your eyes wide open as we journey further into the world of atoms and their colorful secrets. Welcome back, students. Hello again, curious minds. As we continue our exploration of the flame test and emission spectra, we're about to uncover a truly remarkable aspect of science. Get ready to unravel the world of emission spectra and atomic fingerprints. You see, when we look at the light emitted by elements through a device called a spectroscope, we find something astonishing: a series of discrete lines of light, each corresponding to a specific wavelength. These patterns of light are unique to each element, like a secret code written in colors. We call this an emission spectrum, and it's like an atomic fingerprint that can tell us which elements are present in a substance. Imagine being able to identify elements just by observing the light they emit. This insight has profound implications not only in the realm of chemistry but also in fields like astronomy, where scientists use emission spectra to study the composition of stars and galaxies. The technique even finds applications in identifying elements in unknown substances, helping us solve intriguing mysteries. So, as we journey forward, keep in mind that light isn't just illumination. It's a window into the atomic world, revealing the hidden identities of elements all around us. Ready to explore more? Let's journey further into the captivating realm of light and atoms. Hello again. Welcome back, inquisitive learners. Our journey through the world of flame tests and emission spectra continues with a focus on the practical applications that emerge from this scientific wonder. Imagine a tool that enables us to analyze the elemental composition of substances with stunning accuracy. That's exactly what emission spectra provide us. In industries, we harness this knowledge for quality control purposes, ensuring that products meet the desired standards. Whether it's detecting impurities in materials or verifying the correctness of chemical compositions, emission spectra play a vital role. Beyond Earth's surface, astronomers have found a treasure trove in emission spectra. By studying the light emitted by distant stars and galaxies, they can decipher the composition of these celestial bodies, giving us insights into the universe's grand tapestry. And let's not forget about the incredible advancements in spectroscopy technology. From visible light to ultraviolet and infrared, these technologies allow us to uncover even more mysteries, expanding our understanding of the atomic and molecular world. As we wrap up our journey today, remember that the seemingly simple act of observing light can lead to profound discoveries, changing how we view the cosmos and our own world. So, let's celebrate the power of science and continue exploring the incredible ways it shapes our understanding of the universe. Welcome back. Good day, students. Today, we're going to delve into the intriguing world of alkali metal ions and their roles in both chemistry and human physiology. To begin, let's discuss how these ions usually behave in chemical reactions. As we've learned, alkali metal ions tend to have a less active role in most reactions, often acting as spectators. This is particularly true for their salts, which are generally soluble in water. However, there are exceptions, such as reactions involving the alkali metals in their elemental forms, like those found in equations 7.16 through 7.21. Now, let's move on to their role in the human body. Good day, students. Continuing on our journey, let's explore how alkali metal ions, particularly sodium and potassium ions, play an indispensable role in human physiology. These ions become major components of essential bodily fluids. For instance, sodium ions are a significant presence in blood plasma, while potassium ions reside in intracellular fluid. The concentrations of these electrolytes, around 0.1 m, are crucial for maintaining the ionic balance necessary for normal cellular function. These ions act as vital charge carriers, enabling various cellular processes to occur seamlessly. Continuing on. Alright, class, let's gather round and discuss a fascinating topic today. Lithium elixir. I want you all to listen carefully as we dive into the remarkable properties of this substance. First of all, let's emphasize the importance of lithium. It's a chemical element with the symbol Li and atomic number 3. Now, class, pay close attention to this. Lithium is incredibly light. But what truly makes it fascinating is its use in various applications. From medicine to batteries, lithium plays a crucial role. Now, remember, students, the term elixir suggests a magical solution. So when we talk about the lithium elixir, we're referring to its potential to revolutionize energy storage and improve mental health treatments. Now, I encourage you all to explore further and grasp the significance of lithium in our world. Class dismissed for now. Alright, class. Now, let's turn our attention to an intriguing aspect of alkali metal ions. While sodium and potassium ions serve crucial functions, the lithium ion takes a unique stance. Unlike its counterparts, the lithium ion has no known function in normal human physiology. Yet, throughout history, it has captured people's imaginations. Since its discovery in 1817, salts of lithium were often associated with almost mystical healing abilities. Some even claimed that these ions were present in ancient «fountain of youth» formulas. A curious historical fact: back in 1927, a soft drink containing lithium was introduced by C. L. Grigg. Originally named Bib Label Lithiated Lemon Lime Soda, it later became the more familiar 7UP. Let's move forward to learn more. Now, Hello, dear students. Today, we're going to delve into an intriguing historical connection between a soft drink and mental health. Our journey takes us back to the early 1950s when the U.S. Food and Drug Administration made a decision that had a significant impact. They chose to remove lithium from 7UP due to their concerns. Now, the fascinating twist here is that, almost simultaneously, psychiatrists made a groundbreaking discovery about the therapeutic effects of lithium ions on a mental condition known as bipolar disorder. This disorder leads to intense mood swings, ranging from deep depression to manic euphoria. And guess what? The lithium ion steps in as a sort of mood stabilizer, smoothing out these extreme mood shifts. This intervention actually helps individuals with bipolar disorder lead more effective lives in their day-to-day activities. As we proceed, you'll see how the world of chemistry can have unexpected connections to our daily experiences. Hello, dear Welcome back, students. Let's dive deeper into the world of bipolar disorder and the roller coaster of emotions that come with it. Bipolar disorder is a mental condition characterized by drastic mood swings. On one end of the spectrum, individuals experience deep, overwhelming depression, making it hard for them to find joy or motivation. On the other end, they swing into manic euphoria, where their energy, thoughts, and behaviors become excessively heightened. These mood shifts can be incredibly challenging for those who suffer from bipolar disorder, making everyday life quite a struggle. This is where our hero, the lithium ion, comes into play. It helps level out these extreme highs and lows, offering a sense of stability. Welcome back, students. Hello again, curious minds. Now, let's dig into the science behind lithium's therapeutic role in managing bipolar disorder. This humble lithium ion has proven to be quite the game-changer. By interacting with brain chemistry, it actually stabilizes those intense mood swings that characterize bipolar disorder. Imagine a seesaw. Lithium helps to balance it out, making the highs less extreme and the lows more manageable. This stabilization allows individuals with bipolar disorder to function more effectively in their daily lives. The effect of lithium on brain chemistry showcases the powerful interplay between chemistry and our well-being. Hello again. Greetings, inquisitive learners. Our exploration of lithium's journey doesn't just end with the medical world. It highlights the captivating interplay between chemistry and mental health. Who would have thought that a chemical element like lithium could have such a profound impact on our emotional well-being? This connection reminds us of the intricate ways in which science intersects with our lives. The bridge between chemistry and medicine is a powerful one, emphasizing the importance of interdisciplinary knowledge. As we conclude our discussion on lithium, let's keep in mind that our understanding of chemistry can lead to discoveries that touch even the most unexpected aspects of our existence. Greetings. Dear students, we're arriving at the culmination of our journey today. Reflect on the incredible connection we've explored, the removal of lithium from and its subsequent role in treating bipolar disorder. This serves as a vivid example of unintended consequences leading to remarkable discoveries. While the removal of lithium from impacted the beverage industry, it inadvertently led to groundbreaking research and treatment in the mental health field. This serves as a reminder that the web of knowledge is woven intricately, and science often reveals its most captivating surprises when we least expect it. As we close this chapter, remember that the world of chemistry holds countless hidden connections waiting to be explored. Dear students, Good day, students. Today's lesson is going to take us on an intriguing journey into the world of serendipitous discoveries and the surprising impact of lithium ions. Our story begins in the 1940s with Australian psychiatrist John Cade, who was actually researching the use of uric acid, a component found in urine, to treat manic depressive illness. Quite unexpectedly, while administering uric acid to manic laboratory animals, something remarkable happened. Many of the manic symptoms seemed to vanish. As further investigation unfolded, it turned out that uric acid wasn't responsible for this change, but rather, it was the lithium ions present. Now, let's delve deeper into this fascinating tale. Good day, student. Welcome back, students. Our journey continues with the realization that it wasn't uric acid, but the lithium ions themselves that were responsible for the observed reduction in manic symptoms. This revelation marked a significant turning point in psychiatric research. As scientists understood the potential benefits of lithium, they transitioned from using uric acid to administering lithium salts. However, it's important to note that while lithium demonstrated promising antipsychotic effects, there were also serious concerns. Lithium overdose could lead to severe side effects, including kidney failure and even death. This raised a crucial question. How could the therapeutic benefits of lithium be harnessed while minimizing its risks? Let's move on to uncover more. Welcome back, students. Hello again, students. The journey of lithium's acceptance and integration into psychiatric treatment was not a swift one. Despite its potential benefits, lithium salts were not approved as antipsychotic drugs for human use until 1970. The challenge lay in finding ways to safely administer lithium to reap its therapeutic effects without exposing patients to harmful side effects. Fortunately, progress was made in developing safer methods of administration. Today, lithium is primarily administered orally in the form of lithium carbonate, known as E2CO3. This active ingredient can be found in prescription drugs like Escalith, which has played a vital role in treating certain psychiatric conditions. Now, let's explore the positive impact of lithium on patients with bipolar disorder. Hello again, Hello, dear students. Today, we're delving into an intriguing historical tidbit that connects chemistry, health claims, and a popular soft drink. Our focus now turns to the beverage 7UP registered. Back in the day, this soft drink actually contained a lithium salt, which was believed to provide various health benefits. These benefits included claims of increased energy, enthusiasm, and even cosmetic enhancements like a clear complexion, lustrous hair, and shining eyes. It's fascinating how chemistry found its way into the world of beverages, isn't it? However, in the early 1950s, around the time when the antipsychotic properties of lithium were discovered, the lithium content was removed from 7UP registered. The connection between lithium and its antipsychotic effects marked a turning point in both chemistry and medicine. Now, let's journey forward as we explore more captivating examples of how chemistry shapes the world around us. Hello, dear Greetings, students. Our journey through chemistry's influence continues, and this time, we're focusing on the chemistry within your favorite soft drinks. Have you ever wondered what makes these drinks bubbly and refreshing? It's all about chemical reactions. Soft drinks are composed of various chemical components. One key process is carbonation, where carbon dioxide, CO2, is dissolved in the liquid. This leads to the formation of carbonic acid, giving the drink its characteristic tangy taste. But that's not all. These acids also play a role in preserving the beverage. Chemistry truly is everywhere, even in the most everyday things we enjoy. Keep your curious minds engaged as we move forward. Greetings, students. Welcome back, attentive scholars. Our exploration of chemistry's reach brings us to a mouthwatering topic: taste perception. As you savor your favorite soft drink, remember that your taste buds are hard at work. Taste receptors on your tongue interact with the chemistry of the drink. Acids, sugars, and various flavor compounds come together to create the delightful sensory experience you perceive as sweet, sour, and fizzy tastes. Isn't it fascinating how chemistry plays a fundamental role in the way we experience flavor? Let's continue our journey of discovery. Welcome back. Hello again, inquisitive minds. Our path through the realm of chemistry now leads us to antioxidants and beverages. Antioxidants are remarkable chemical compounds that play a protective role in our bodies. They help prevent oxidation, which can lead to cell damage. You might find antioxidants in various beverages like teas and fruit juices. These compounds, such as polyphenols and vitamins, contribute to the vibrant colors and healthful properties of these drinks. So, next time you enjoy a cup of tea or a glass of juice, remember the chemistry at play, safeguarding your cells and well-being. Let's keep exploring the dynamic world of chemistry. Hello again. Great to see you all engaged, students. Our journey through chemistry continues with a focus on the chemistry of carbonated beverages. Have you ever wondered how those bubbles get into your favorite drinks? Carbon dioxide, the same gas we exhale, is responsible. It dissolves in liquids due to its solubility. The carbonation process reaches an equilibrium, where the gas concentration is balanced between the liquid and the air inside the bottle or can. This equilibrium leads to the formation of carbonic acid, contributing to the unique taste of these beverages. Also, consider the impact of temperature. Colder liquids can hold more dissolved CO2, resulting in fizzier drinks. It's all about the chemistry of equilibrium and solubility. Stay curious, as our exploration unfolds. Great to see you all in. Hello, eager learners. Today, we're uncovering the captivating chemistry behind bubbles. Ever wondered how those delightful bubbles form in your sparkling beverages? It's a remarkable process. During carbonation, tiny gas bubbles form on what we call nucleation sites. These sites can be imperfections on the surface of the container or even tiny particles suspended in the liquid. As more gas is dissolved in the liquid, these bubbles grow and eventually rise to the surface, creating that effervescent experience you enjoy. So, the next time you're mesmerized by the dance of bubbles in your drink, remember that it's all about chemistry at play. Let's keep the excitement going as we delve further into the world of chemical wonders. Hello, eager. Good day, students. Today, we're delving into the intriguing realm of noble gases and their unique properties. Let's begin by understanding what sets these elements apart. Noble gases, found in Group 18 of the periodic table, possess some remarkable characteristics. One key feature is their fully filled s and p subshells, which make their electron configurations exceptionally stable. This stability is reflected in their large first ionization energies, which is the energy required to remove the outermost electron. As we move down the column, we notice a predictable decrease in ionization energy. But what's truly fascinating about noble gases is their reactivity, or rather, their lack of it. Due to their stable electron configurations, they are remarkably unreactive, earning them the name, inert gases, for quite some time. It was in the early 1960s that a breakthrough occurred, challenging this perception. Neil Bartlett, a researcher at the University of British Columbia, had an intriguing idea. He proposed that xenon, Z, an element from this group, might have a low enough ionization energy to actually form compounds. This was a groundbreaking concept that led to the discovery of noble gas compounds and expanded our understanding of chemical reactivity. So, remember, even the most stable elements can surprise us with their hidden potential for chemical interactions. Let's explore further. Good day, students. Hello, dear students. Today, we're delving into a fascinating realm where the simplest of elements plays a crucial role in the treatment of a destructive psychiatric disorder. Our topic of focus is the remarkable lithium-ion. Even in this era of advanced drug design and biotechnology, lithium-ion stands out as one of the most effective treatments for this disorder. What's truly astonishing is that, despite years of intensive research, scientists are still grappling with the full understanding of how lithium's biochemical action leads to its therapeutic effects. Now, let's unravel the mysteries behind this phenomenon. Hello, dear students. Alright, my curious learners. Let's journey deeper into the world of lithium-ion. Due to its resemblance to sodium, lithium-ion finds its way into our blood plasma. This incorporation into our circulatory system has a notable impact on the behavior of nerve and muscle cells. But why does lithium behave this way? Well, here's a little secret. The smaller radius of lithium compared to sodium brings about a unique interaction between lithium and molecules within our cells. Let's move on to explore further. Alright. Welcome to the intricacies of cellular interactions, dear students. When it comes to lithium-ion, its smaller radius compared to sodium-ion leads to a different type of interaction with the molecules in our cells. This unique behavior gives rise to unconventional effects on various molecular processes. Understanding this distinct interaction is a puzzle that researchers are still trying to solve. Keep your curiosity alive as we journey onwards. Welcome to the Let's explore the intricate world of neurotransmitters, shall we? Our studies have revealed that lithium-ion has a significant influence on these vital messengers of our nervous system. It's known to alter the function of certain neurotransmitters. This alteration might just be the key to understanding why lithium is effective as an antipsychotic drug. The connection between its effects on neurotransmitters and its therapeutic properties is an exciting avenue of ongoing research. Let's explore. Welcome back, students. Today, we're delving into another fascinating topic: the alkaline earth metals. Just like the alkali metals we discussed earlier, the alkaline earth metals exhibit some unique traits. Let's uncover their characteristics together. At room temperature, these elements exist as solids, and they display typical metallic properties. However, there are notable differences when compared to their alkali metal counterparts. Alkaline earth metals are known to be harder and denser, and they possess higher melting points. This means they require more heat to transition from solid to liquid compared to alkali metals. Now, let's dive deeper into the specifics of these intriguing elements. Welcome back, students. Hello again, young minds. Let's take a closer look at the metallic nature of alkaline earth metals. Just like other metals, they exhibit exceptional characteristics. These include the ability to conduct electricity and heat, which makes them essential for various applications. Moreover, these metals have a distinctive shine, known as luster, which gives them that polished appearance. Remember, they maintain their solid form even at room temperature. This solid-state property sets them apart from other elements that might exist as gases or liquids at the same conditions. Hello again, young. Greetings, inquisitive minds. Let's embark on a journey into the world of material properties. Alkaline earth metals stand out due to their remarkable hardness and density. When compared to alkali metals, they are noticeably harder. This means they are more resistant to being scratched or dented. Additionally, alkaline earth metals are denser, meaning they have a greater mass packed into the same volume. This characteristic plays a significant role in shaping their overall physical properties. Imagine how these factors contribute to the way these elements behave and interact with their surroundings. Greetings. Hello, bright minds. Let's continue our exploration of alkaline earth metals by focusing on their thermal behavior. One standout characteristic is their higher melting points compared to alkali metals. This means that these metals need more energy input to change from a solid to a liquid state. Imagine heating these elements to elevated temperatures before they can transform. This aspect has important implications for their applications, as materials with high melting points are often used in scenarios where heat resistance is crucial. So, as we journey through the world of chemistry, keep in mind how the melting behavior of elements can influence their role in our lives. Hello, bright. Hello again, dear students. Today, we're diving into the intriguing world of elements and their reactivity. Our discussion starts with a comparison between alkaline earth metals and alkali metals in terms of their first ionization energies. While the ionization energies of alkaline earth metals are lower than those of alkali metals, they're not as low. This difference in ionization energies leads to an interesting trend in reactivity. Alkaline earth metals are actually less reactive than their alkali metal neighbors. Remember, this reactivity is linked to how easily elements lose electrons. As we journey across a period in the periodic table, the ease of electron loss decreases. However, when we move down a group, the ease of electron loss increases. This is a key principle in understanding the reactivity of elements. Specifically, beryllium and magnesium, being the lightest alkaline earth metals, exhibit the lowest reactivity within this group. Now, let's continue our exploration into the world of chemistry and discover more about these fascinating patterns. Hello again, dear. Hello again, young scholars. Today, we're diving into the fascinating realm of how alkaline earth metals interact with water. We've learned that these metals display a captivating trend of increasing reactivity within their group. But let's start with an exception: beryllium. This metal stands out by not reacting at all with either water or steam, even when heated to high temperatures. Quite the anomaly, isn't it? Now, let's focus on magnesium. Unlike beryllium, magnesium does react, but the reaction is slow when it comes into contact with liquid water. However, when steam is introduced, things change. The reaction becomes more vigorous, resulting in the formation of magnesium oxide and hydrogen gas. This equation, Mg plus H2O right pointing arrow MgO plus H2, captures the essence of the process. So, isn't it fascinating how different elements within a group can behave so uniquely? Keep this thought in mind as we move forward. Hello again, young. Welcome back, students. Today, we're delving into the fascinating world of chemical reactions involving calcium and water. As we've learned, calcium and the elements positioned below it in the periodic table have an intriguing reactivity with water. While their reactivity is slower when compared to the highly reactive alkali metals, it's still a remarkable process. Let's look closely at the reaction between calcium and water, depicted in Figure 7.25. The balanced chemical equation for this reaction is Ca(S) plus 2H2O L. Right pointing arrow calcium hydroxide 2 Aq plus H2 G. This equation represents the transformation of calcium and water into calcium hydroxide in aqueous form and hydrogen gas. The interaction may be slower, but it's a crucial concept in our exploration of chemical reactions. Welcome back, students. Greetings, curious minds. Today, we're delving deeper into the specifics of the calcium-water reaction. In this captivating process, calcium displaces hydrogen from water. The result? The creation of calcium hydroxide and the release of hydrogen gas. Picture this: calcium swooping in and taking the place of hydrogen in water molecules. This displacement is the heart of the reaction we're exploring. Moreover, the produced calcium hydroxide isn't just any compound, it's a base. When it dissolves in water, it forms a solution that's on the basic end of the pH scale. Keep in mind that this reaction is a testament to the captivating interactions that occur at the atomic level. Greetings, Hello, inquisitive minds. Let's explore a crucial factor influencing the calcium-water reaction: the surface area of calcium. Just like how you might dissolve sugar faster by stirring it into smaller pieces, the reaction rate of calcium with water is also affected by its surface area. The more finely divided the calcium is, the faster the reaction takes place. Why is that? Well, smaller calcium particles provide more contact points for water molecules to interact with, leading to a speedier reaction. It's a fantastic example of how the microscopic details impact the overall outcome of a chemical reaction. Hello. Good day, future chemists. Our exploration of the calcium-water reaction wouldn't be complete without a look at its practical applications. Have you ever wondered how those self-heating meals work? Or how hand warmers provide cozy comfort on chilly days? Well, you can thank the calcium-water reaction for that. This reaction's controlled rate of heat production is harnessed in self-heating food and chemical heat packs. Manufacturers utilize this phenomenon to create convenient, portable sources of warmth. It's an example of science lending its hand to everyday comfort and convenience. Good day, future. Hello, dear students. Today, we're about to uncover a fundamental pattern in the reactivity of a group of elements known as the alkaline earth elements. Prepare to delve into the intriguing world of chemical reactions and electron behavior. In equations 7.22 and 7.23, we're presented with a fascinating insight. These alkaline earth elements have a common tendency. Can you guess what it is? They have a penchant for shedding not just one, but two of their outer s electrons. This unique behavior results in the formation of ions with a charge of 2+. Picture this as a sort of elemental transformation. As we move forward, we'll explore specific examples that highlight this behavior in action. Hello, dear students. Let's now zoom in on magnesium, one of the alkaline earth elements, and its intriguing behavior in chemical reactions. When magnesium encounters chlorine at room temperature, an exciting dance unfolds. The magnesium atoms willingly engage in a reaction, resulting in the creation of a compound called magnesium chloride, chemically denoted as Mgcl. This reaction is eloquently captured in equation UFR. Just imagine these two elements combining, and through their interaction, a new substance is born. It's almost like witnessing a miniature explosion of chemical creativity. Let's switch gears to another awe-inspiring phenomenon involving magnesium. Imagine the spectacle of magnesium burning with dazzling brilliance in the presence of air. This combustion is nothing short of breathtaking, and it leads to the formation of a substance known as magnesium oxide, or MgO for short. The equation 7.25 beautifully captures this combustion reaction, where magnesium couples with oxygen to create this new compound. The intense light and heat produced during this process illustrate the incredible energy transformations that chemical reactions can unleash. Let's switch gears. As we wrap up this enlightening journey, it's important to grasp the overarching essence of the reactivity pattern we've explored. Alkaline earth elements, as a group, exhibit a shared inclination to part with two of their outer s electrons. This daring move results in the formation of 2+ ions, which in turn shape their chemical interactions. The captivating examples of magnesium's reactions, forming magnesium chloride and magnesium oxide, are concrete manifestations of this reactivity pattern. So, why is this knowledge valuable? Well, it provides us with insights into the behavior of these elements in various situations, whether it's chemical reactions in a lab or the dazzling combustion of magnesium. This connection between fundamental principles and real-world occurrences is what makes chemistry truly fascinating. As we wrap up. Hello again, dear students. Today, we're delving into a captivating phenomenon known as the flame test, a method used to identify elements based on the colors they emit when heated in a hot flame. Our focus turns to alkaline earth ions and the colors they unveil. When heavier, alkaline earth ions are introduced to the flame, they gift us with characteristic colors that are truly remarkable. For instance, strontium salts ignite a dazzling red hue, gracing the skies with their presence during fireworks displays. On the other hand, barium salts add a touch of nature's green to the spectacle. The vibrant colors you witness are a result of the unique energy transitions occurring within the atoms of these elements. Isn't it amazing how we can unveil the elemental identities just by observing the shades of light they release? Now, let's continue our exploration into the mesmerizing world of chemical phenomena. Hello again, dear. Welcome back, students. Our journey takes us further into the atomic realm, where energy levels within atoms hold the key to the colors we witness during flame tests. Here's the thing. Atoms have distinct energy levels that electrons can occupy. When these electrons jump from one energy level to another, they either absorb or emit light. Imagine it like a mini light show happening within each atom. The specific colors we see are a direct result of these electron transitions and the energy they release. This is why when we introduce certain elements into a hot flame, their characteristic colors emerge, helping us identify them with precision. As we delve deeper into the relationship between atomic energy levels and the hues we perceive, remember, it's all about the dance of electrons and the captivating play of light. Onward to more enlightening discoveries. Welcome back, students. Hello once again, attentive scholars. Let's focus our attention on a particular alkaline earth element that paints the night skies with its radiant hue, strontium. When strontium salts are introduced into the heart of a flame, they showcase their brilliance by emitting a spectacular red color. The magic behind this lies in the energy transitions that unfold within strontium's atomic structure. As electrons make their leaps between energy levels, they release energy in the form of light, specifically in the red part of the visible spectrum. This unique phenomenon is what gives fireworks their dazzling red bursts, captivating our eyes and hearts during celebrations. Strontium's red is a testament to the intricate dance of particles and energy, creating a visual symphony that brings joy to our senses. As we appreciate the beauty of science in action, let's continue our expedition through the world of chemical wonders. Hello once again. Greetings, inquisitive minds. Our journey wouldn't be complete without exploring another captivating element that adds its touch to the palette of firework colors: barium. Barium salts, when subjected to the intense heat of a flame, gift us with an enchanting green glow. This ethereal coloration is the result of precise electron transitions occurring within barium's atomic structure. As electrons journey between energy levels, they release energy in the form of light, specifically in the green segment of the visible spectrum. This radiant green display elevates firework shows, giving them an additional layer of aesthetic delight. The chemistry behind these colors is truly a marvel, showcasing how nature's building blocks can craft astonishing beauty. With each burst of green in the night sky, remember the intricate symphony of atoms and energy working harmoniously. Onwards, my curious learners, to more illuminating revelations. Greetings. Good day, students. Today's topic delves into the fascinating world of elements that are not only abundant on Earth, but also play crucial roles in supporting life. We'll be focusing on two remarkable elements, magnesium and calcium. Just like their neighbors sodium and potassium, these elements are found in relatively high amounts on our planet, and are even present in seawater. But what makes them truly intriguing is their vital role as cations in ionic compounds. These compounds are fundamental building blocks for various processes within living organisms. Now, let's zoom in on calcium, which holds a special place in the realm of human health. Calcium isn't just any element. It's particularly crucial for the growth and maintenance of our bones and teeth. The next time you smile or take a step, remember the importance of these elements working behind the scenes. Let's explore further. Good day, student. Welcome back, students. Let's delve deeper into the abundance and significance of magnesium and calcium. These elements aren't just randomly present. They're relatively abundant in both Earth's crust and the vast expanse of seawater. What makes them stand out is their incredible ability to form ionic compounds. Now, what are those, you ask? Well, ionic compounds are structures formed by the combination of positively charged ions, cations, and negatively charged ions, anions. These compounds serve as building blocks for countless processes within living organisms. Just like pieces of a puzzle, these ionic compounds contribute to the functioning of cells, tissues, and even the entire body. Magnesium and calcium are key players in this intricate web of life. Let's move on to unravel more about their significance. Welcome back, students. Great job staying engaged, students. Now, let's zoom in on calcium, an element that truly deserves our attention. When we talk about calcium, we're not just talking about another element. We're talking about a fundamental building block for our bodies. Calcium plays a pivotal role in maintaining our health. You know those strong bones and teeth that keep us standing tall and flashing those smiles? Calcium is a key player in their growth and maintenance. But that's not all. Calcium also flexes its muscles, quite literally. It's essential for muscle contraction, ensuring that every move we make is possible. And if you're wondering how we feel sensations or respond to stimuli, calcium has got a hand in that too. Nerve transmission relies on the availability of calcium ions. So, you see, calcium isn't just a passive element. It's actively contributing to our daily lives. Keep up the great work, and let's continue our journey. Great job staying. Fantastic progress, students. As we've been exploring the captivating world of magnesium and calcium, you might be wondering, how do these elements fit into the bigger picture of life? Well, it's time to connect the dots. Magnesium and calcium aren't just isolated elements. They're intricately woven into the fabric of life. They contribute to the construction of cells, tissues, and organs that make up our bodies. From the cellular level to the systemic level, these elements are indispensable. Just like a symphony relies on each instrument playing its part, our bodies rely on the harmonious interplay of elements like magnesium and calcium. They help maintain balance within our internal environment, a state known as homeostasis, which is crucial for our overall health. So, the next time you consider the elements that make life possible, remember the vital roles played by magnesium and calcium. Well done, everyone. Fantastic progress. Bravo, students. We've journeyed through the captivating world of magnesium and calcium, two elements that are more than just names on the periodic table. They are foundational to life as we know it. From their abundance on Earth to their significance in our bodies, magnesium and calcium are at the heart of life's machinery. We've explored their roles in forming ionic compounds, contributing to bone and teeth health, facilitating muscle movement, and aiding nerve transmission. As we conclude today's lesson, I encourage you to marvel at the intricate dance of elements and the incredible web of connections they create. Keep your curiosity alive, as there's always more to discover in the world of science. Until next time, keep exploring and learning. Bravo, student! Hello, dear students. Today, we're delving into the intriguing journey of hydrogen gas, from its discovery to its unique properties. Our exploration begins in the 17th century with Robert Boyle, who first observed hydrogen while experimenting with dilute acid and iron filings. Remarkably, it took another 90 years for Henry Cavendish to recognize hydrogen as a completely new substance. He coined the term, flammable air, to describe it. However, it was Antoine Lavoisier who finally gave this remarkable gas its official name, hydrogen, in 1783. Lavoisier's insight came when he noticed that hydrogen could burn in the presence of air, forming water. The name itself carries significance, as it originates from the Greek words, hydro, meaning water, and genes, meaning creator. Imagine the excitement and curiosity these scientists must have felt during these discoveries. Let's continue our journey through the captivating world of chemical reactions and their outcomes. Hello, dear Greetings, young minds. As we venture further into the realm of hydrogen, let's focus on a captivating aspect: its combustion and water formation. You see, when hydrogen combines with oxygen from the air, a fascinating reaction takes place. This reaction produces water, a compound essential for life as we know it. The chemical equation for this reaction is 2 sub plus O right pointing arrow 2 sub O. Isn't it remarkable how two simple elements can give rise to something as vital as water? Beyond its role in forming water, hydrogen also plays a crucial part in energy production. It's a key player in combustion reactions, releasing energy in the process. As we uncover more about hydrogen's unique properties, remember that even the simplest elements hold immense potential for understanding the world around us. Greetings, young. Welcome back, eager learners. Our exploration of hydrogen wouldn't be complete without delving into its significance in energy applications. Prepare to be amazed, for hydrogen isn't just any gas, it's a clean and incredibly versatile energy source. In a world striving for sustainability, hydrogen shows promise as a potential replacement for fossil fuels in various sectors. One exciting technology involving hydrogen is the hydrogen fuel cell. These cells operate by combining hydrogen with oxygen from the air, producing electricity in the process. The best part? The only byproduct of this reaction is water, making it an environmentally friendly solution. Hydrogen fuel cells offer advantages such as high efficiency, quiet operation, and zero emissions. As we peer into the horizon of energy possibilities, keep in mind that hydrogen's journey is far from over. There's so much more to uncover and learn about this remarkable element. Welcome back, dear students. As we wrap up our exploration of hydrogen, let's take a moment to reflect on its symbolism and future prospects. Hydrogen isn't just a gas, it's a symbol of the relentless pursuit of scientific understanding. Its discovery and subsequent studies have provided invaluable insights into chemical reactions and the world of energy. Looking forward, hydrogen holds the potential to revolutionize our energy systems. Its clean and abundant nature makes it a prime candidate for addressing pressing environmental challenges. Researchers and innovators worldwide are actively working on harnessing hydrogen's power for various applications. So, as we conclude this chapter on hydrogen, remember that its story is intricately woven into the fabric of scientific progress and holds the promise of a brighter, more sustainable future. Stay curious and keep exploring the wonders of chemistry and energy. Dear students. Hello, students. Today, we're delving into a captivating chapter in the history of air travel, focusing on the use of hydrogen gas in early airships. As you might know, hydrogen, being the lightest element, seemed like a perfect choice for these pioneering aircraft that emerged around the year 1900. However, there was a significant challenge lurking within this choice: the highly flammable nature of hydrogen itself. This characteristic led to a tragic incident that changed the course of airship travel forever. On 6 May in 1937, disaster struck the Hindenburg airship. While attempting to dock at Lakehurst, New Jersey, the Hindenburg burst into flames. Imagine the scene. Journalists were present to cover the airship's maiden flight from Europe to the USA. The entire disaster unfolded within a mere 90 seconds, leaving no doubt about the dangers of using hydrogen in this context. This devastating event marked the end of an era in commercial airship travel. Now, let's move on and explore more about the early days of air travel and the lessons learned from this tragic event. Hello, students. Hello, dear students. Today, we're going to delve into the intriguing world of hydrogen chemistry. You might recall our previous discussions about alkali metals, which lose their outer ns1 electron to form cations. Interestingly, hydrogen's electron configuration, 1s1, suggests a connection to alkali metals chemistry. Despite this, hydrogen's chemistry is far more diverse and intricate. The reason for this complexity lies in hydrogen's ionization energy, which stands at a remarkable 1,312 kJ per mole. This value surpasses that of any metal and is even comparable to oxygen's ionization energy. As a consequence, hydrogen stands as a nonmetal. Although hydrogen's electron configuration mirrors alkali metals, its chemistry is distinct due to the elevated ionization energy. This element is renowned for existing as a colorless diatomic gas, H2, in most conditions. Let's journey further into the captivating world of hydrogen's chemistry. Hello, dear students. Welcome back, everyone. Let's explore hydrogen's electron configuration in more detail. Hydrogen, with its 1s1 electron arrangement, bears a striking resemblance to the electron configurations of alkali metals, characterized by the ns1 configuration. This similarity suggests that hydrogen, like alkali metals, has the potential to lose its outermost electron to attain a more stable state. When hydrogen loses its lone electron, it transforms into a positively charged ion, also known as a cation. This intriguing resemblance sets the stage for the diverse chemistry that hydrogen exhibits. Welcome back, everyone. Hello again, eager learners. Today, we're peeling back the layers of hydrogen's chemistry complexity. Although hydrogen shares a surface-level similarity with alkali metals, its chemistry is notably more intricate. The primary factor driving this complexity is hydrogen's significantly higher ionization energy. This energy barrier opens the door to multiple potential electron configurations and diverse chemical behavior. Hydrogen forms a multitude of compounds with various elements, contributing to its central role in a wide array of chemical reactions. This intricate dance of electrons and atoms brings about a fascinating tapestry of hydrogen's chemical interactions. Hello again. Great job staying engaged, everyone. Let's uncover more about hydrogen's identity. Thanks to its distinctive characteristics, hydrogen earns its classification as a nonmetal. Factors such as its ionization energy and electronegativity solidify this status. Notably, hydrogen exhibits a remarkable property by existing as a colorless diatomic gas, known as H2, under typical conditions. The bonding between two hydrogen atoms gives rise to this gaseous molecule. As we explore further, you'll come to appreciate the elegance and intricacy of hydrogen's role in the chemical world. Great job staying. Good day, students. Today's lesson is all about the captivating reactivity of hydrogen with nonmetals. It's fascinating how hydrogen behaves differently compared to alkali metals. While alkali metals readily give away their electrons, hydrogen holds onto its electron tightly. When hydrogen encounters nonmetals, something remarkable happens. It forms molecular compounds by sharing its electron with the nonmetal, unlike alkali metals that typically undergo complete electron transfer. Think of this as a unique electron dance between hydrogen and nonmetals. Let's take a closer look at this process and its implications. Good day, students. To better understand hydrogen's behavior, let's contrast it with an example from the alkali metals. Sodium, an alkali metal, reacts vigorously with chlorine gas. The result is the formation of an ionic compound called sodium chloride, sodium chloride. In this reaction, the outermost electron of sodium is completely transferred to a chlorine atom. This is a classic case of electron exchange, leading to the creation of sodium chloride. The energy change associated with this reaction is delta H equals -410.9 kilojoules. This starkly contrasts with hydrogen's behavior, which we will delve into next. To better understand. Now, let's shift our focus to the intriguing world of hydrogen's interactions with nonmetals. Unlike alkali metals, hydrogen prefers to keep a firm grip on its electron. When hydrogen meets nonmetals, they engage in a different kind of chemical dance. Instead of a complete electron transfer, hydrogen and nonmetals share electrons to form molecular compounds. This is a unique aspect of hydrogen's behavior, setting it apart from other elements. Imagine this as a partnership where electrons are shared, leading to the creation of new compounds. Let's explore the implications of this fascinating phenomenon. Now, let's shift. As we've discovered, hydrogen's tendency to share electrons with nonmetals opens up a world of possibilities. This behavior leads to the creation of a wide range of molecular compounds, each with its own unique properties and applications. This is a stark departure from the electron transfer commonly seen with alkali metals. This insight into hydrogen's behavior provides us with a deeper understanding of chemical reactivity and the intricate ways elements interact. Remember, these interactions shape the world around us, influencing everything from the materials we use to the reactions that power various processes. Keep exploring and questioning, as the world of chemistry holds countless wonders waiting to be uncovered. As we've discovered. Good day, students. Welcome to another exciting lesson in chemistry. Today, we're delving into the remarkable world of hydrogen and its ability to form molecular compounds with nonmetals. As we explore this topic, you'll see just how versatile and essential hydrogen is in the realm of chemistry. Our journey begins with the formation of some familiar compounds: water, ammonia, and methane. These compounds are created when hydrogen bonds with other nonmetals. Take water, for example. Its molecular formula, HO, reflects the combination of two hydrogen atoms with one oxygen atom. Similarly, in ammonia, NH, and methane, CH, hydrogen forms bonds with nitrogen and carbon, respectively. Now, let's consider the bigger picture. The ability of hydrogen to bond with carbon is of utmost importance in the realm of organic chemistry. We'll dive deeper into this concept in our upcoming chapters. So, get ready to unravel the mysteries of hydrogen's role in forming bonds and driving chemical reactions. Good day, students. Hello again, dear students. Today, we're delving into the fascinating world of hydrogen's behavior in the presence of water. As you know, hydrogen has a unique ability to form H+ ions, where it loses an electron. This phenomenon is particularly prominent when hydrogen reacts with nonmetals to create acids when dissolved in water. Let's consider the example of hydrogen chloride gas. When it interacts with water, a remarkable process occurs. The electron of the hydrogen atom is transferred to the chlorine atom, leading to the formation of hydrochloric acid, HCl aqueous. In this solution, you'll find H+ and chloride ions, and they're comfortably surrounded by water molecules. This ability of hydrogen compounds to create acids in water is a crucial aspect of aqueous chemistry. And remember, we'll dive deeper into the world of acids and bases in later chapters. Keep up the curiosity. Hello again, dear. Welcome back, eager minds. Today, we're unraveling the importance of aqueous chemistry, where hydrogen compounds play a starring role. As we discussed earlier, hydrogen's tendency to form H+ ions when immersed in water is remarkable. Think of HCl gas dissolving in water. The process involves the transfer of an electron from hydrogen to chlorine, resulting in the creation of HCl opening parenthesis AQ closing parenthesis. This solution contains H+1AQ2 and Cl2 ions, nestled within the embrace of water molecules. Now, why is this significant? Well, this ability of hydrogen compounds to generate acids when in contact with nonmetals has wide-ranging implications in the realm of chemical reactions. It's a fundamental concept that you'll encounter repeatedly in your journey through chemistry. So, stay curious and let's keep exploring. Welcome back. Good day, inquisitive minds. Get ready for a sneak peek into our upcoming adventures. We're on the brink of diving into the intricate world of acids and bases. This exciting exploration is just around the corner, specifically in Chapter 16. So, what's in store? We'll be delving deep into the chemistry of acids and bases, essential substances that you'll encounter throughout your studies. Acids, as you'll learn, release H+ ions, while bases release O ions. Understanding the behaviors of acids and bases is crucial for unraveling the complexities of chemical reactions. So, keep your curiosity alive as we embark on this exciting journey into the world of acids, bases, and their remarkable properties. Good day. Welcome back, everyone. Today, we're delving into the intriguing characteristics of hydrogen, particularly its interaction with metals. As we've learned, hydrogen, a nonmetal, exhibits a distinctive trait shared by nonmetals: the ability to acquire electrons from metals with low ionization energy. This process leads to the formation of intriguing compounds, such as solid metal hydrides containing the hydride ion, H. Remember equation 7.16 that showcased how hydrogen reacts with active metals? This emphasizes hydrogen's nonmetal behavior. Rather than behaving like an alkali metal, hydrogen showcases its affinity for electron gain. This serves as yet another example of how diverse and captivating the world of chemistry can be. Now, let's journey further into the intricacies of hydrogen's properties. Welcome back. Hello, curious minds. Our exploration continues with a closer look at metal hydrides and the fascinating electron exchange that occurs. When hydrogen gains electrons from metals, it forms metal hydrides. These compounds hold a unique structure, with the inclusion of hydride ions, H-. This interaction brings about electron exchange, which contributes to enhanced stability within the compounds. This stability arises from the electrostatic interactions that occur between the positively charged metal cations and the negatively charged hydride ions. This is yet another testament to the intricate dance of particles and forces within the world of chemistry. Let's proceed to unravel more about this enthralling process. Hello, curious. Greetings, young scientists. Our journey through hydrogen's mysteries leads us to a crucial comparison between hydrogen's behavior and that of alkali metals. As we've witnessed, hydrogen's ability to gain electrons aligns it much more closely with nonmetals than with alkali metals. This contrast reveals the depth of the periodic table's intricacies and showcases how a single element can display such diverse behaviors based on its position. This concept underlines the fundamental principles of chemistry and the captivating patterns we find within the elements. Stay curious as we continue our exploration of hydrogen's unique properties. Greetings. Good day, students. In today's lesson, we're delving into the fascinating world of Group 16 elements, also known as the oxygen group. As we journey down this group, we observe a captivating transformation from non-metallic to metallic character. Now, let's take a closer look at the individual members. Oxygen, sulfur, and selenium are classic examples of nonmetals within this group. On the other hand, tellurium exhibits properties of a metalloid, and there's polonium, a highly rare and radioactive metal. An interesting point to note is that while oxygen presents itself as a colorless gas at room temperature, the remaining members, sulfur, selenium, tellurium, and polonium, are all solid. Now, let's explore further the physical properties of these Group 16 elements. Good day, student. Hello, eager learners. Today, we're unraveling the intriguing transformation from non-metallic to metallic character within Group 16 elements. As we journey down the group, we encounter oxygen, sulfur, and selenium, exemplifying non-metallic properties. However, as we venture further, a gradual shift to metallic characteristics becomes evident. Take tellurium, for instance. It stands as an intermediate, showcasing properties of both metals and nonmetals, and is classified as a metalloid. Lastly, we have polonium, a metal that's not only rare but also radioactive. This dynamic range of characteristics within a single group underscores the diversity and complexity of the periodic table. Stay tuned, as we continue our exploration. Hello, eager Well done, my enthusiastic learners. We've journeyed through the captivating realm of Group 16 elements, uncovering a rich tapestry of properties and characteristics. From oxygen's gaseous state to the solidity of sulfur, selenium, tellurium, and polonium, these elements each hold a unique place within the periodic table. The transition from non-metallic to metallic character as we descend the group offers us valuable insights into the periodic trends that shape the behavior of elements. The presence of metalloids like tellurium and the intrigue of radioactive metals like polonium remind us of the remarkable diversity that exists in the world of chemistry. Keep in mind that these elements, with their distinct attributes, contribute to the intricate puzzle that is the periodic table. Thank you for joining me on this enlightening journey. Until next time. Well done, my. Welcome back, curious minds. Let's dive deeper into the world of fluorine's reactivity. We have here two equations that exemplify fluorine's electron transfer prowess. In the first equation, fluorine interacts with water, and you can see that it leads to the formation of hydrofluoric acid and oxygen gas. Notably, this process liberates a whopping -758.9 kJ of energy. In the second equation, fluorine interacts with silicon dioxide, resulting in the creation of silicon tetrafluoride and oxygen. This reaction releases -704.0 kJ of energy. Remember, the minus sign indicates that these reactions are exothermic, releasing heat in the process. Fascinating, isn't it? Let's keep our scientific curiosity ignited as we move forward. Welcome back. Great job keeping up, everyone. Let's delve deeper into oxygen's significance. Did you know that roughly 21% of the air we breathe is made up of OCHEM molecules? This makes oxygen an integral part of the atmosphere and absolutely essential for supporting life on Earth. From humans to animals and plants, we all rely on this oxygen to thrive. Just think about how incredible it is that a single element plays such a vital role in shaping our planet's ecosystems and the living beings within them. Great job keeping up. Good day, students. Today, we're delving into the intriguing realm of noble gases and their unique properties. Let's begin by understanding what sets these elements apart. Noble gases, found in Group 18 of the periodic table, possess some remarkable characteristics. One key feature is their fully filled s and p subshells, which make their electron configurations exceptionally stable. This stability is reflected in their large first ionization energies, which is the energy required to remove the outermost electron. As we move down the column, we notice a predictable decrease in ionization energy. But what's truly fascinating about noble gases is their reactivity, or rather, their lack of it. Due to their stable electron configurations, they are remarkably unreactive, earning them the name, inert gases, for quite some time. It was in the early 1960s that a breakthrough occurred, challenging this perception. Neil Bartlett, a researcher at the University of British Columbia, had an intriguing idea. He proposed that xenon, Z, an element from this group, might have a low enough ionization energy to actually form compounds. This was a groundbreaking concept that led to the discovery of noble gas compounds and expanded our understanding of chemical reactivity. So, remember, even the most stable elements can surprise us with their hidden potential for chemical interactions. Let's explore further. Good day, students. Hello again, students. Today, we're diving deeper into the captivating world of chemical interactions, specifically focusing on oxygen's electron affinity and the fascinating process of oxide formation. Now, what's remarkable about oxygen is its strong tendency to attract electrons from other elements, which is a process we call oxidation. When oxygen combines with metals, it often takes the form of the oxide ion, denoted as O2. This ion has a unique noble gas configuration that lends it exceptional stability. Just imagine the electrons swirling around, rearranging themselves in a way that makes this oxide ion particularly content. But that's not all. We also see that the formation of nonmetal oxides can be incredibly exothermic, meaning it releases a significant amount of energy. This exothermic nature makes the process energetically favorable. Keep in mind, as we journey through these concepts, that the dance of electrons and the stability of these ions are what drive these interactions. Now, let's delve further into the intricacies of oxygen's role in chemical reactions. Hello again, Hello, dear students. Today, we're delving into a fascinating realm of oxygen anions and their intriguing compounds. In our previous discussions about alkali metals, we highlighted two less common oxygen anions, the peroxide ion, oxide da-ion, and the superoxide ion, oxide da-ion. These ions form compounds that lead to interesting reactions, ultimately producing oxide and oxygen. Let's take a closer look at one such reaction. 2H2O2 in aqueous solution transforms into 2H2O in liquid form and O2 in gaseous state. And guess what? This reaction is exothermic, meaning it releases energy. The enthalpy change, increment HO for this reaction is -1926 kJ. So, as you can see, chemical reactions can be accompanied by energy changes, and that's what we'll explore further. Hello, dear Welcome back, students. Today's journey leads us to another intriguing element, sulfur. Now, sulfur doesn't just come in one form. It exhibits various allotropic forms. These are different structural arrangements of the same element. But the most common and stable form of sulfur that we'll focus on is the yellow solid with the molecular formula S8. This solid sulfur molecule is quite fascinating. It's composed of an 8-membered ring of sulfur atoms, forming a unique structure. Although in reality, sulfur consists of these S8 rings, for the sake of simplicity in chemical equations, we often represent it as just S when referring to the solid form. Welcome back, students. Hello again, young minds. As we continue our exploration of sulfur, let's touch upon a fundamental concept, stoichiometry. This term refers to the quantitative relationship between reactants and products in a chemical reaction. Now, when it comes to chemical equations involving sulfur, we often simplify the representation. Even though solid sulfur is actually made up of those intriguing S8 rings we discussed, we commonly write it as just S in chemical equations. This simplification doesn't alter the essence of the reaction. It's done to make equations clearer and calculations easier. Remember, the world of chemistry is full of these practical strategies to help us better understand and work with complex reactions. Hello again, young. Welcome back, students. Today, we're delving into the intriguing world of sulfur and its fascinating chemical properties. Just like oxygen, sulfur exhibits a tendency to acquire electrons from other elements, resulting in the formation of sulfides which carry the Su- ion. Interestingly, most sulfur in nature exists as metal sulfides, which play a significant role in various processes. While sulfur shares similarities with oxygen, it stands below oxygen in the periodic table, and its inclination to form sulfide anions isn't as strong as oxygen's tendency to form oxide ions. This distinction contributes to the greater complexity of sulfur's chemistry when compared to oxygen's behavior. For instance, sulfur and its compounds, found in resources like coal and petroleum, can undergo combustion when exposed to oxygen. This reaction yields sulfur dioxide, a notable air pollutant. Let's explore further as we uncover the intricacies of sulfur's chemistry. Welcome back, students. Now, let's turn our attention to an element that follows sulfur in group 16 of the periodic table, selenium, symbol Se. This relatively rare element holds a unique position as it's considered an essential trace element for life. In small quantities, selenium plays a crucial role in various biological processes. However, it's important to note that selenium can be toxic at higher doses. Selenium boasts a variety of allotropes, with some forms resembling the famous S8 ring structure seen in sulfur. Its atomic arrangement contributes to its distinct properties. As we explore further, remember that selenium's role in life's processes makes it a fascinating element to study. Now, our journey continues with another intriguing element. Tellurium, denoted by the symbol tellurium. Positioned below selenium in group 16, tellurium introduces us to a world of structural complexity. Its elemental structure involves long, twisted chains of tellurium bonds, a feature that sets it apart from its predecessors in this group. This structural arrangement contributes to tellurium's distinct properties and behaviors. Just like sulfur, selenium, oxygen, and sulfur, Tellurium is also prone to adopting the -2 oxidation state. This pattern offers us valuable insights into the recurring chemical trends within this group. As we explore the depths of tellurium's intricacies, remember that its properties emerge from its atomic structure and bonding patterns. Our journey continues. Hello again, dear students. Today, we're diving into the intriguing world of Group 16 elements and their fascinating properties. As we move from oxygen to sulfur, then to selenium and finally to tellurium, a notable pattern emerges. These elements form progressively larger molecules and exhibit increasing metallic properties. But let's focus on an interesting aspect: thermal stability. When these elements combine with hydrogen, we observe a trend in thermal stability down the column. Starting with water, H2O, which stands as the most stable compound, followed by H2S, H2Se, and finally, H2Te. This trend indicates that the thermal stability decreases as we move down the group. Now, let's explore the mechanisms behind these trends and delve deeper into the properties of Group 16 elements. Hello again, dear. Hello, students. Today, we're diving into an intriguing group of elements known as the halogens. These elements, found in Group 17 of the periodic table, exhibit some fascinating properties that we're about to explore. Now, remember, we'll be focusing on the halogens excluding astatine, as its properties are not well understood due to its rarity and radioactivity. And even less is known about tennessine, a recently discovered element. So, let's take a closer look at these halogens and their properties. Hello, students. Alright, dear students, let's dig deeper into the properties of these intriguing halogens. Group 17 consists of 4 elements: fluorine, chlorine, bromine, and iodine. These elements are highly reactive due to their possession of 7 valence electrons, just one shy of a stable octet. Their reactivity primarily stems from their strong desire to gain that one extra electron. This characteristic makes halogens quite reactive with other elements, forming various compounds. Additionally, these elements are often found in nature as diatomic molecules, pairs of atoms. They exist as gases, like fluorine and chlorine, or even as solids, like iodine, at room temperature. Alright, dear. Now, students, let's talk about the outliers in this group. First, we have astatine, an element that's extremely rare and radioactive. Due to its scarcity and radioactivity, we don't have a complete understanding of its properties. On the other hand, we have tennessine, a relatively recent discovery. This element is highly synthetic, meaning it's artificially created in labs. Since it's a newcomer to the periodic table, scientists are still in the process of studying its properties. As we continue our exploration of these elements, remember that the periodic table holds a wealth of information that helps us understand the building blocks of matter. Thank you for your attention, and keep up the great work. Now, students. Welcome back, dear students. Today, we're delving into the fascinating world of halogens. Unlike the Group 16 elements, which exhibit different characteristics, all the halogens we've studied so far are nonmetals. Now, here's an interesting trend. As we move along the periodic table from top to bottom, the melting and boiling points of these halogens increase. This means that fluorine and chlorine, with their lower atomic numbers, are in the gaseous state at room temperature. Bromine, on the other hand, has a higher atomic number and exists as a liquid. Lastly, iodine, with an even higher atomic number, is found in its solid form. And here's a fun fact. Each of these halogens exists as diatomic molecules, which means they form pairs F2, Cl2, bridge 2, and I2. Visualize this as a molecular duet. Now, let's move on to our next intriguing topic. Welcome back, dear. Hello, dear students. Today, we're delving into the intriguing world of halogens and their electron affinities. As we explore, we'll uncover the dominant chemistry driven by their unique tendency to acquire electrons from other elements, forming halide ions, symbolized as X-. Remember, X can represent any halogen element. Now, when it comes to reactivity, we observe a pattern. Fluorine and chlorine stand out as more reactive compared to bromine and iodine. In fact, Fluorine is an electron-hungry element that eagerly snatches electrons from various substances it encounters. This process, often exothermic, results in fascinating chemical reactions. Let's take a look at a couple of examples to grasp this concept better. Hello, dear students. Great to have you back, students. Today, we're focusing on fluorine's electron affinity and its remarkable reactivity. Because of fluorine's strong negative electron affinity, it's like a magnet for electrons. When fluorine encounters substances like water, it seizes electrons with enthusiasm. This process is usually accompanied by the release of energy, making it exothermic. This means that when fluorine interacts with substances like water, a significant amount of heat is produced. Let's look at a couple of examples that illustrate this exciting behavior. Great to have you back. Welcome back, curious minds. Let's dive deeper into the world of fluorine's reactivity. We have here two equations that exemplify fluorine's electron transfer prowess. In the first equation, fluorine interacts with water, and you can see that it leads to the formation of hydrofluoric acid and oxygen gas. Notably, this process liberates a whopping negative 758.9 kilojoules of energy. In the second equation, fluorine interacts with silicon dioxide, resulting in the creation of silicon tetrafluoride and oxygen. This reaction releases negative 704.0 kilojoules of energy. Remember, the minus sign indicates that these reactions are exothermic, releasing heat in the process. Fascinating, isn't it? Let's keep our scientific curiosity ignited as we move forward. Welcome back, dear students. In today's exploration, we're delving into the fascinating realm of halogens and their intriguing properties. Let's start by discussing fluorine gas. It's known to be quite challenging and dangerous to work with in a laboratory setting due to its unique characteristics. The need for specialized equipment underscores the complexities involved. On the other hand, we have chlorine, the most industrially significant halogen. What sets chlorine apart is its usability and importance in various industries. Have you ever wondered how chlorine is produced? It's an exciting process called electrolysis. In this method, an electrical current is utilized to trigger the oxidation of chloride anions, resulting in the formation of molecular chlorine, chlor. Unlike fluorine, chlorine reacts slowly with water, forming stable aqueous solutions of hydroxychloride and hypochlorous acid, also known as hypochlorous acid. This chemical reaction is quite intriguing, showcasing the reactivity of chlorine in a distinct manner. Now, let's explore more about these reactions and their underlying principles. Welcome back, dear. Hello again, students. Let's delve into the intriguing properties of chlorine and its multifaceted roles. Firstly, chlorine is often employed to purify drinking water and maintain the cleanliness of swimming pools. The magic happens when chlorine reacts with water, producing a compound known as HOCl or hypochlorous acid. This HOCl is a powerful disinfectant that helps eliminate harmful microorganisms. Now, another fascinating aspect of chlorine's behavior is its interaction with metals. When halogens like chlorine come into contact with most metals, they engage in direct reactions, forming compounds known as ionic halides. This showcases the reactivity and versatility of these elements. Additionally, the halogens showcase their affinity for hydrogen as well. When halogens react with hydrogen, they form gaseous compounds called hydrogen halides. For instance, let's take a look at the reaction between hydrogen and chlorine. H2 gas plus Cl2 gas gives us 2 molecules of HCl gas. This is a prime example of how chemical reactions can lead to the formation of new substances with distinctive properties. Let's move forward and explore more captivating examples of chemical interactions. Hello again, Hello, dear students. Today, our exploration takes us into the realm of hydrohalic acids and their intriguing solubility properties. These compounds exhibit a remarkable trait: they are all highly soluble in water. When they dissolve, they give rise to what we call hydrohalic acids. As you might remember from our earlier discussions, hydrohalic acids are an important category of acids that have distinct characteristics. Specifically, we have HCl, HBr, Hi, and HF as notable examples. Now, pay attention to this distinction. HCl, HBr, and high are considered strong acids due to their remarkable ability to completely ionize in water, releasing a high concentration of hydrogen ions. On the other hand, HF is classified as a weak acid, as it only partially ionizes in water, releasing fewer hydrogen ions. This distinction in strength has significant implications for their behavior in various reactions. So, as we move forward, keep these details in mind to deepen your understanding of acids and their fascinating properties. Hello, dear students. Welcome back, dear students. Today, we're delving into the intriguing world of chemistry once again. Our focus shifts to a group of elements known as the noble gases, residing in group 18 of the periodic table. These gases are unique in various aspects. Firstly, they're nonmetals, and interestingly, they exist as gases even at room temperature. Now, here's a fascinating fact. Unlike many elements that combine to form molecules, the noble gases stand alone as single atoms. Imagine that. To get a clearer picture of their characteristics, let's refer to Table 7.8, which outlines some of their important physical properties. However, as we explore these elements, we must note a slight limitation. The radioactive nature of radon, which is the noble gas with the highest atomic number, 86, has restricted the extent of our study into its reaction chemistry and certain properties. Nevertheless, this won't stop us from uncovering the wonders of the noble gases. Welcome back, dear. Good day, students. Today, we're delving into the intriguing realm of noble gases and their unique properties. Let's begin by understanding what sets these elements apart. Noble gases, found in group 18 of the periodic table, possess some remarkable characteristics. One key feature is their fully filled s and p subshells, which make their electron configurations exceptionally stable. This stability is reflected in their large first ionization energies, which is the energy required to remove the outermost electron. As we move down the column, we notice a predictable decrease in ionization energy. But what's truly fascinating about noble gases is their reactivity, or rather, their lack of it. Due to their stable electron configurations, they are remarkably unreactive, earning them the name, inert gases, for quite some time. It was in the early 1960s that a breakthrough occurred, challenging this perception. Neil Bartlett, a researcher at the University of British Columbia, had an intriguing idea. He proposed that xenon, Z, an element from this group, might have a low enough ionization energy to actually form compounds. This was a groundbreaking concept that led to the discovery of noble gas compounds and expanded our understanding of chemical reactivity. So, remember, even the most stable elements can surprise us with their hidden potential for chemical interactions. Let's explore further. Good day, students.